Thank you. Thanks. So yeah, we will need to finish at 10:15 because I have a flight to catch. It's probably good news or bad news. I don't know, but right. So maybe this is a bit too loud. This. Right. So yesterday we what did we do? We did a few things, but we ended up talking about signature kernels at the end. And so in particular, we had this integral relation between k phi xy st and the shifted kernel, which was of this form. So this is over u from 0 to s, and this is v from 0 to t of k phi plus, where phi plus is the shifted by one weighting function over the same path uv, and then inner product dxu dyv in v. Okay, so so a priori this is not computable. I mean, easily computable because the right-hand side and left-hand side are two different functions of time. But for some cases, this is. So for example, the first case, phi k equals to a constant, and for simplicity, let's take 1. We saw that, of course, the right-hand side and left-hand side are the same function, so this becomes actually a differential equation. And so assuming, for example, you know, that x and y are differentiable, then we can differentiate both sides of this equation by first s and then t, or the other way around, and get this PD, right? That I ended the, so this is k, let's call this k1. So this is just the weight function equals 1. So kx, y, st, s dt, k, sorry, 1, x, y, st. And here, because these are differentiable, you can put x prime, s, y prime, t in B. Okay? And so we have shifted the problem of evaluating, so just as a reminder, k phi of xy is the inner product of the signature of x with the signature of y according to this phi weighted inner product. Okay? So we've shifted the problem of computing this a priori complicated you know, function of taking the inner product between two infinite dimensional signatures to a problem of solving a two-dimensional PD, right? Right, and so then there are various ways of solving this this PD, and that I'm not going to focus too much on, but you can, so you can, for example, if x and y are straight line, you can find the closed form solution, an analytic solution of this PD, so you can solve it exactly. Otherwise, you know, finite difference schemes can be built to do so. Right. So then one question might be, okay, so if are there any other nice weighting functions that we can choose and compute this object? And so there are a few examples. So the one that I want to look at, so this is from the paper by Tom, Sokas, Lyons, Osteri, and someone else that now I don't remember the name. So this is not very good, sorry. But I don't, there is a third person that was a Tom postdoc, but I don't remember the name. 23, I think. Right, so this example, so there are several examples. There are more or less all of this form. So they consist in taking, so let pi be a real valued function. So a real valued probability measure. So a real valued random variable. Okay. And then let's consider weights of this form. So phi of k. So let's suppose that this pi is valued in the positive real line, right? So it's r plus. Just you can do it in r, but it's slightly more involved. So r plus valued random variable, and then you take phi k to be the kth moment, expectation of phi to the k. Okay. If you take this type of weight function, then what happens? Then you have k phi xy. So I'm not going to write st all the time, but k phi xy. So this is equal to so what is it? This is the sum I equals 0 to infinity of phi k. So in this case, it's expectation of pi to the k. And then you have now the inner product between the ith level of the signature of x with the ith level of the signature of y, right? And this is an inner product in the ith tensor power of v. Now, because once again, things in terms of the signature decay very fast, we can exchange expectation and sum by Beanies or dominated convergence. And so in the end, what we get is that we get something of the form expectation of sum I equals 0 to infinity pi I. Let me put pi I inside the first inner product. So inner product of pi to the I signature. So this is expectation over pi, of course. Huh? This is pi. Signature of x to ith level, and then you have signature of y ith level, inner product in the tensor I. And then essentially what happens is the following: is that if you take a path, okay, and you rescale it by a constant, right? So if you have a path x, you rescale it by a constant. Let's call it lambda, right? Lambda times x. So you multiply every point of the path by lambda, and then you take the signature. What you get is that you will rescale each level of the signature by lambda to the power that level. Okay, so you get a series of tensors of the form lambda 1 in the first level, then lambda times the first level of the original signature, so of x, and then you have lambda squared signature of x at level 2, and so on, right? So rescaling the path by, it's like the determinant, right, in some sense. Rescaling the path by a scalar rescales each level by the appropriate power. And so here you see that what you get by doing that is just that you get an expectation over pi of the sum I equals 0 to infinity of the signature of pi x at level I, inner product with the signature of y at level I, the tensor I. And then and then the inner part of the expectation, the inside the expectation, is just the definition of the original signature kernel, right? So the one with the weight equals to 1. And so what you end up doing, you end up taking an expectation of a rescaled version, well, of K1. So this is the one that solves the PDE, K1 of a rescaled path x, y. Okay, so that's essentially what happens. And so here in practice, what happens is that you can compute this object by sampling from pi, right? Rescaling the path, solving the PDE, and averaging. Okay? And so, this can be computed via Monte Carlo, or actually, because this is a real valued function, there, you can use quadrature. As well, okay? Right, so this is another example of computation that you can do. Right. So then, what do I want to talk about? Yes. So maybe because we don't have a huge amount of time, what we need, I really want to touch on the machine learning application at the end. So yeah, this part, this last quality here. Yeah, so if you do this manipulation and you use the fact that the signature of a path rescaled by lambda is equal to the original signature, where each level is rescaled by lambda to the power the level, then you can put the pi to the I inside the signature, and what you end up with is that inside the expectation you have the definition of the original or the vanilla signature kernel, the one that solves the PDE, but applied to a rescaled version of the path. So yeah, and so then you can compute this reweighted signature kernel by averaging PDEs. You can compute a PDE that's on a rescaled path, then you sample from the scale, you rescale the path, and then you average. Yeah. So very expensive. Like very expensive computation, yes. But yeah. Yes.
It only works if if the moments are finite and some converges, right? And you can do Fubini and blah blah blah. But the point is you start from two paths, and then you need to find some distribution which allows you to do that. Right?
Absolutely, yes. So that's a very good point. What I forgot to say is the assumption here. So we need that this satisfies this assumption star, right? That so do you remember yesterday this summability condition, right? So that the sum of, I think it was phi k c to the k over k factorial squared is finite. So you need to pick a random variable on real valid, like the exponential works, for example, such that it decays fast enough. Yes. Yeah. Thanks. Right. So, okay. So then, so Christian already talked about reproducing kernel Hilbert spaces in his talk 2 days ago. But you know, we need this space, right? So reproducing. So let me just do a very quick recap of what is a reproducing kernel Hilbert space. So a reproducing kernel Hilbert space is simply a Hilbert space H. A Hilbert space of functions, so functions from a set X into R, such that the evaluation functionals, so the functionals that to F associates the evaluation of F at X, so this is the evaluation functional at X, is continuous, right? Is continuous in this space, right? So that there exists, so such that F of X is less than C of X, F in H, where C is a constant, so C of X, 0, constant, for all F, for all in H, for all X in X. Okay, so this is an abstract definition of an RKHS, and a priori, it's where is the kernel, right? So here is the kernel. So you know, if you use just the Riesz representation theorem, you know, it's clear that for any F you can find, so there exists a unique linear functional, there exists a unique functional in the Hilbert space, and let me call it K sub X in the Hilbert space, such that the evaluation of F at X is equal to the inner product of K X with F. Right, so this is, and so this is all. This is often these properties in the kernel in the kernel literature is called the representer. No, the reproducing property. Reproducing property. And so, of course, then if you take f to be ky, where k is defined in the same way but evaluated at y, then this yields a function k of two variable, k x comma y, which is defined as the inner product. So this is the inner product in H, inner product between kx and ky in H. So that's your kernel. So if you have an RKHS defined in this abstract way, there is clearly a unique kernel associated to it. Now, the hardest question is, if I give you a kernel, is there a unique RKHS associated to it? And the answer is no, a priori in general. But if you assume that the kernel is positive semi-definite, so if you give me a kernel, if a kernel is PSD, positive semi-definite, yeah, so the positive semi-definite, I guess, don't need to define this, then there exists a unique RKHS. So Hilbert space functions that have this reproducing property associated to K. To the kernel K. And this is a deep theorem. So this is called the Moore-Arons-Jean theorem. That it proves in the 50s, I think. Right, and this is a functional analytic result. Anyway, right. So if you have a kernel, at least the minimal, a good requirement to use that kernel, and the first requirement from that kernel to be used in a context of machine learning is to check that it's positive semi-definite, right? And so if we go back to the signature kernel, so for the signature kernel we have k phi. What do we have? So let's check that this is positive semi-definite. So what happens? So you give yourself n scalars, and then you try and compute the I guess the double sum. Write it once, but this is double ij alpha I alpha j signature kernel weighted by a weight function phi, evaluated at the path xi and xj, right? So what is this? This is by definition is equal to the double sum ij alpha I alpha j signature of x, the whole signature of xi with the whole signature of xj, and this is the the product in you remember this is the phi product, inner product, and then so then I can put the alpha I inside the respective things. So this becomes, let me just rewrite it in one go, so this is alpha I inner product with alpha j phi, and then I can put also the sums inside. So that's so this will become the inner product of sum over I of alpha I s of xi with sum over j alpha j s of xj in phi, and this is equal to the norm of the sum over the sum over I alpha I signature of xi norm in this. So this is the norm in this Hilbert space here. So the completion that we defined yesterday. T phi squared, and this is positive. Right? So the signature kernel is positive semi-definite, therefore there exists a unique signature kernel reproducing kernel Hilbert space associated to it. Okay. And we will denote, so definition, will denote H sub phi, the corresponding RHS. Right, so we have two, so just to recap, by now we have two Hilbert spaces, right? So we have the first, so we have two Hilbert spaces. We have T phi, right? T phi of V. This is where the signatures live, right? And this was obtained by as the completion of T of V by the inner product phi. And then we have the reproducing kernel Hilbert space H phi associated to the signature kernel, right? Using this construction of Moore-Arons-Jean. So these are two different Hilbert spaces, but you know, there is a theorem that you can prove, but I'm not going to do it. But there's a theorem that tells you that for any element of the reproducing kernel Hilbert space H phi, there exists a unique element in L sub f in the Hilbert space T phi of V, such that for any path x, we have f of x is equal to the inner product between L, F, and the signature of x in phi. Okay, so and furthermore, essentially the the map that associates L sub f to f is an isomorphism of Hilbert spaces. And so essentially, this is I think is a nice way of somehow reconciling the results from the previous section, the one on signatures, and this next section, this on kernels, right? Because essentially, what this is saying is that linear functionals on the signature that we saw, they were universal, so they had this nice approximation property, are essentially the same thing, are in an isomorphic relation with elements in the RHS of the signature kernel. So these two spaces are isomorphic. Now, in the previous in the previous section, what we saw is that we looked at T1, right? We look at the inner product was somehow weighted by 1. We were just looking at signatures. In this case, we have a more general class of functionals, right? Functions on paths. This H phi are functions on paths that are indexed by this weight phi. So we have a whole class of different functions on paths that are indexed by phi. So we don't have one signature kernel; we have many. And so then there are several results, and so then you would, as you would expect, so the H phi is universal. So this is another theorem, I guess, that you prove exactly, very similar to the the one that we saw yesterday. So if I'm not going to write the details, but essentially H phi is universal. So if you take a compact set, you restrict H phi to this compact set, and then you take the uniform closure of this. This gives you all continuous functions on this compact set, right? So the RHS has the same nice universal approximation properties. So this is universal approximation. Approx. As linear functionals on the signature. The advantage, I don't know if it's an advantage or not, is that here we have a whole class of linear functions, a whole class of functionals on paths that we can use in the context of learning. And then the question becomes, how do you choose phi, right? For example, what's the phi that is more appropriate?
Actually, I have it. You have results like this for all the spaces and just continuous, the alpha holder.
The continuous paths.
So suppose that instead of continuous functions on K, I'm interested in universal approximation for alpha holder functions on K.
Yes, but not me, but in general in approximation theory there are, but not uniform. You don't use the uniform norm. You have L2, for example, where you can also discontinuous functions, right? Where you can average over the jumps, but you need to change the norm. Yeah, sorry. This is so K is a subset of path space compact.
One question regarding the first theorem. So not every element of T phi of V is a signature, right?
No.
So is there an interpretation when you pass to the limit on the right-hand side in, using a sequence of signatures, passing to the limit to an element of T phi, which is not a signature? What would happen at the level of the RKHS?
So sorry, you want to take a limit?
Yes. So the limit in X. So I take a sequence of signatures.
Okay.
Understood as elements of T phi.
Yeah.
And pass to a limit which is not a signature.
Yeah.
I can do that, right?
Yeah.
Is there an interpretation of that being some kind of closure of H phi in some bigger norm or some?
I think that this is essentially how you prove this theorem. Is that essentially you get power series of in signatures. So we know essentially this theorem relies on the fact that we know that signature spans the tensor algebra, but they span somehow the finite linear combination of signatures give you a generic tensors. But actually, you can extend this result to an infinite linear combinations of signatures. So you actually have a series. So I think that's the main ingredient of that is needed in this result. So you get really to prove this result, you really have this power series of kernel evaluations, weighted kernel evaluations, but it's an infinite sum, and that converges, and that's how you prove this. I don't know if this answers more or less. More or less, yes. We can talk offline, yes, with the more details. Yeah. Right. So understanding how the different RKHSs with different choices of phi interacts with each other, which is smaller, which is bigger, what one does contain, what the other doesn't, it's an open question, right? So this is, I think, it's quite a cool area to work on. But we have some examples. So let me give you one quick example of an element that belong to one RKHS, but that doesn't belong to another. Okay, so this is this example. So you take a differential equation. This is an example. So you take a differential equation of this form, dyt is equal to, okay, let me write it, f d gamma t times yt, started at, okay, so this is a matrix valued differential equation. So y0 is the identity in, this is the identity in the n times n matrix space. And f, okay, f gamma is a path with values in some Banach space, and f of x is equal to this matrix. So it's 0, x transpose, and then we have big 0 here. Okay? And this is in n by n matrices. So F here is a map from RD. Let's suppose that gamma lives in RD. So F is a map from RD into R n times n. Okay, and so this this type of equation is known in some literature as the hyperbolic development, because it's essentially a type of Cartan development of the path into an hyperbolic space, but we don't care about the geometric structure in this example. And then so then if you solve this differential equation, you can solve this differential equation at between 0 and 1. And then you can evaluate the solution matrix in one of the entries. So you can look at the path at the map that map the path gamma to the solution of this differential equation at 1. So this is a matrix, and I select the last entry, the NN entry, right? And so this map here, let's call it phi. This map here is belongs to what? Well, you show that this belongs to continuous functions on unparameterized paths to R. Okay, so this is a function. You can show that this, this is a function that is invariant to reparameterizations, and this generalized version of reparameterizations. So it induces a map continuous function on unparameterized paths gamma. So this is actually an equivalence class, but let's not complicate things too much, into R. Okay, so this is just the solution map of this differential equation. And so then, so this is a map that was used, for example, by Terry and Ben Ambly to prove their results in 2010. And but actually, what Tom and Terry and co-authors showed is that this map psi can be realized in the following interesting way. So psi is equal to the inner product of something with the signature of gamma between 0 and 1. So let me not write this, according to a weight function phi that I will write in a second. And the linear functional that is here is the expected signature of Brownian motion. The expected signature. This is the expected Stratonovich signature. So this is the expected signature of Brownian motion. This B is Brownian motion between 0 and 1. Okay. And where phi k is equal to 2 to the k over 2 times the gamma function of k over 2 factorial. Okay? So you can realize this function on path space as a linear function on the signature. This is not very surprising, but this linear function on the signature, the linear part is the expected Stratonovich, expected signature of Brownian motion in this, where the integrals are interpreted in the Stratonovich sense. Yes.
But that the product on the right hand side, I mean the explication of the signal motion.
Yeah.
It's like, as a computation, what turns out is all the elements are the form, or t to the power whatever divided by factorial power. So the expected information, or the statement says there is a probability space with a Brownian motion such that I have this.
Okay, so yes. Okay, so the expected signature of Brownian motion is a deterministic object, right?
Exactly.
Yeah. So essentially, what the result tells you that the function on path space that is induced by this differential equation, right, by this hyperbolic development, can be realized as a linear functional on the signature of the driving path gamma, where the linear functional that acts on the signature is the expected signature of Brownian motion.
But it's just, in a way, just a coincidence that the form of the signature is exactly the form of a signature of Brownian motion. Or the form of these elements.
The form of this linear.
Yeah.
Yeah. I mean, yes, it is a coincidence.
Statement is not a probabilistic statement.
It's not a probabilistic statement. Well, I mean, the probabilistic statement is the following: is that now the expected signature of Brownian motion is something like this. So we have formulae for this, right? So you can.
Yeah.
So this is equal to.
Yeah, but the fact that it appears in this inner product somehow a coincidence.
Hold on. I don't remember. EI. So I think this is the Fawcett lines or Fawcett Victoire. Sorry. So yeah. So I mean, the probabilistic statement it's here, right? Is that the expected signature has this form, and now you have a tensor, right, in the tensor space that turns out to be the right one to contract the signature to realize this function.
But it's coincidence somehow.
It's a coincidence. Yeah, I don't know how coincidental it is actually. Yeah, I mean, if you consider a different differential equation, I don't know if this would hold in a similar fashion, but yeah. Yes.
I mean, offering a very speculative probabilistic interpretation. I mean, if we say that the expected signature is something like a Laplace transform, then you put outside the expectation. Is this like a, I don't know, a heat equation for the Laplace transform?
Yeah, but Brownian motion, that's the
Brownian motion. Yeah.
That's the Brownian motion is the surprising thing, right?
Yeah.
It's, yeah, I don't know. The answer is I don't know how generic this time. It's an interesting example, I think, because it has not been pushed more further than this simple example. So yeah, I don't know how general it is, but it's true. And here is the point is that, okay, so the point is that the expected signature of Brownian motion, so expected signature of B, Stratonovich, belongs to T phi of V. So, we know what it is, it's just this. And so this element belongs to T phi of V if you take phi to be, where is it? To take phi to be this special weight function. However, you can prove as an exercise, by contradiction, essentially, that this functional doesn't belong to T1 of V. Okay, so this means that this function on paths is an element of this space, but is not an element of the RKHS associated to the original signature kernel. Right? It cannot be realized as a functional on the simple functional on the signature. Of course, once you have this, so this is an exact. This would be an exact reproducing element, right? So you can reproduce this functional exactly with an element of the RKHS of this RKHS, but not of the other one. However, because we have this theorem, right? We have a universal approximation theorem. We can approximate it, using elements of the original signature kernel RKHS. Yes.
Are these reproducing kernel Hilbert spaces and somehow connected? So if I increase the phi, do I get some inclusion?
Good question. I think this is open.
Oh, really?
How they connect, how they intersect with each other, which is border, which is bigger, what is in one, then it's not in. This is the only example I know that is explicit, that I can say that, you know, I guess from this one you can cook up many others, right? But I think this is an open question to me.
And the T5s are also not.
The T5, sorry?
Okay, stupid question. Wasn't the T5 all just this tensor element such that if I take this norm and multiply with phi of k, that this is finite?
Yeah.
So they should be structured. If I increase the phi, then I have less convergence.
Maybe, yeah, maybe. Maybe. I don't know what you mean by increasing the phi.
So let's say I take a phi tilde, which is bigger than the phi, then I would expect that T phi
For all
tilde.
k.
For all k, yes, yes.
Okay.
Probably.
So it's okay.
Then I would expect that if the T phi tilde of the bigger one is a smaller space than the T phi.
Yeah, this doesn't sound implausible to me.
Okay.
Yeah. Yeah. Right. So yeah. So okay. So what else do I want to say? Maybe I can make a very last comment later. But yeah, I don't know, not straight away. Right. So before getting to the machine, well, now, okay. So this is about approximation. Then, you know, if you talk about kernels, many will refer or will, you know, bring up the notion of characteristicness. Okay? Characteristicness. So so far, what these statements are all statements about functions on paths, right? Approximations of functions on paths. Characteristicness will provide some, you know, some statements about measures on paths. Okay, not functions on paths, but measures on paths. So let me get there quickly. So so kernel is said characteristic if the following holds. So you know, so you have a set. So let's specialize directly on to path space. So let's consider K to be a compact subset of paths. And let's consider, let's denote by PK the space of Borel probability measures. So you have a topology, so probability measures on K. Okay, and then what you can do is that if you take a probability measure, probability measure in this space mu, you know, a measure on paths, what you can associate to this measure, you can associate this object. So you can take the expectation of x sampled from this measure mu of K phi, the phi signature kernel, evaluated at x, comma dot, right? So this is an expectation over the RKHS, right? So this is an element of the RKHS. This belongs to H phi. And this is an expected feature map, right? So this is, you know, you can interpret this expectation in the sense of Bochner. So this is integrals in Hilbert spaces. And yeah, so and this is actually, again, an element of H phi. Okay, so you have a map that takes a probability measure mu and maps it to an element of the RKHS. Okay, and this is usually called a kernel mean embedding. Kernel mean embedding. It embeds a measure into its mean in the RKHS. Right, and so then the definition of a characteristic kernel is said characteristic. So def, so K phi is characteristic if this map is injective. Characteristic if the kernel, or if K ME is injective. Okay, so it's essentially, you know, it's a one-to-one probability measure is one-to-one with the elements of the RKHS. They can be represented as faithfully as elements in the RKHS using this map. Right, and then here is the surprise. So theorem. Universality on compact sets. So on compact sets, but this actually holds in a more general setting. You don't need, but for us, it's compact sets. So universality of a kernel is equivalent to characteristicness. Okay, so a kernel is universal if and only if it's characteristic. So if you have a kernel that like the signature kernel that approximates whose RKHS is dense in space of functions on compact sets, then it's also characteristic. So it means that if you look at the expected kernel map, it can characterize probability measures on paths supported on compact sets. But yeah. Okay, so that's good. So then what do we do with this thing in practice? So here's what we do. So once you have an injective embedding, what you can do, for example, is that if I give you two probability measures, mu and nu, what you can do is that you can map them to something like the difference in RKHS norm between their two kernel mean embeddings. Yeah? So you can do this, and then you can take the expectation over mu x mu k phi x comma dot, and you can compare it to the expectation of y over nu k phi y comma dot. Right. And let's call this d phi. Okay, and this is a metric on compact set. This is a metric, and it's called the maximum mean discrepancy. Maximum mean discrepancy. You know, it's different. You know, it has few properties, like it metrizes the weak topology, for example, on compact sets. It's weaker than the weak topology on non-compact sets. That's not great, but anyway. So it's a distance. It's a similarity measures between probability measures that, because of this characteristicness property, has the following property. So d phi mu nu is equal to 0 if and only if mu is equal to nu. Okay, so that's what it means to essentially. This is the nice consequence of characteristicness, right? That it allows to discriminate the two probability measures in a faithful way, right? And there are several applications for this. For example, you can do hypothesis testing. You can do hypothesis testing on stochastic processes. You can test if two stochastic processes are the same by looking at their MMD. So this is MMD. You can train generative models for time series by taking this distance as a discriminator. Okay, sort of that's another recent application. You can do different things. The question is, okay, can we compute it? Of course, this is always somehow the practical questions. This seems powerful a priori, but can we compute it? And in practice, and the answer is yes. So, you know, you can see that essentially if you take d phi, if you take d phi mu and you square it, that things are easier, then you can see here that what you'll end up with, that you will end up with, you know, just the square of a difference. So you will get 4 terms, right? It will correspond to inner products, and then you can exchange expectation and inner products to essentially get something like this. So you get the expectation over x prime sampled IID from mu, okay, of what? Of k phi x prime. Then you get minus twice the expectation of xy samples from the product measure mu nu of k phi xy. Then you get plus expectation of y prime IID from nu of k phi y prime. Okay, so the squared MMD is the sum of 3 expected kernels. Okay, and then in practice, what happens in practice? You know, if you have x, you have, for example, m sample paths from mu. You know, you have sample paths from mu, and then you have n sample paths from the other measure nu. Then you can build, you know, you can just average. You can use your favorite estimator for the expectation, and so you can get unbiased estimators for d phi. Okay. So essentially, this d phi is just computing a bunch of PDEs many times all around, and then averaging. Essentially, that's how you compute this. Right. So that's that. So maybe a few comments on. Right. So maybe let me spend 2 minutes on. Well, this maybe it's more orally than in writing. So if you don't have compactness, this doesn't work. So you have if you have a nice counterexample that I don't remember what exactly it is, but you have a counterexample, an easy counterexample. It's not a fancy counterexample. If in Chebyrev or browser 23, I think 22. Oh, 22. Yeah, exactly. That's the one. Yes, a counterexample that tells you that if you don't have compactness, this doesn't hold. You don't have this property here. You can't do that. Now there are various ways to restore these nice properties if you don't have compactly supported measures. So one way, and this, by now it has been, this approach has been explored in, not just by the original authors, so Harold and Ilya, but also Luca has a paper on this, and Christian. And so essentially what you can do is that you can renormalize the signature. So you can find the rescaling of the signature that what does is that it allows to ensure that the range of the signature remains bounded inside the tensor algebra. Okay, so you can cook up smart ways of rescaling your paths such that the signature of all these such paths remain in a bounded set, even if the underlying path space is not compact. That's the trick, right? So that's one way of doing it. And so essentially you just modify a little bit the signature, and somehow you get back this type of results. And this is powerful, right? Because when you want to do you want to use this technology, for example, for semi-martingales. These things are usually not compactly supported, so you really need something that does that, right? Then you can always argue in a more machine learning way that if you have a finite set of paths, this is compact, and that's it, right? But and in practice, it's not entirely clear what this renormalization brings as an advantage, but rigorously, that's something that you need. There are other ways. For example, Joseph and Krista, they have this weighted space approach, right? That allows to have this type of results also on non-compact sets. In that case, they don't touch the signature, but they change the topology on path space so that they add a weighting function so that things decay rapidly enough. So that's somehow another way of dealing with the non-compactness issue. And and that's it, right? So that's, yes.
Quick thing to get the perspective. So it looks very attractive to be able to compute the DeFi like that. You use Monte Carlo, but again, for each sample, you have to solve PDEs, right?
Yeah. Yeah, exactly. So here,
to put in perspective the cost, right?
Yeah, that's a good point. So the cost is, okay, so the total cost for evaluating this is going to be the cost of evaluating a PDE times m times n plus, times 3. Let's say m is equal to n. So it's m squared times the cost of evaluating a PDE, and that's it, times 3.
So K phi essentially is a fixed function, right?
Yeah, that's
so
right.
You solve once for it and you save it, and then every time you have to do these things, you cannot. Okay.
You evaluate it on 2 paths, x and x prime.
No, per paths, right?
And every evaluation corresponds to solving a PDE, and then you need to solve as many PDEs as you have pairs paths in your data set, right? So if you have a data set of n paths, you will have n squared PDEs to solve usually, and so that's n.
And the dimension of the PDE essentially here that you're solving is still
2-dimensional.
Yeah. The paths were in 2 dimensions. No, always.
Yeah. It's
okay.
It's linear on the dimension of the path. So okay, so the cost of solving the PDE is, okay, so what is it? Is d, which is the dimension of the paths, where the dimension of v. So this is dim v times so L squared, right? So at least, is this is the length. So if you have time series, right? This is the length. So can't spell length. Length of paths. So it's squared in the length of your time series and linear in the dimension. That's the cost. Then this is the naive cost. There are ways of dropping it, but yeah. So the overall thing is n squared times L squared times t. So if you have very long paths and you have many of them, you're in trouble. But if you have very high dimensional paths and you don't have many of them and they're not that long, it's great. But anyway. Okay, so how do you learn things with this? So here it is. So this is somehow supervised learning. Well, not necessarily supervised, actually. You can do many things. Okay, so learning with these tools. And this is based on essentially what kernel people get excited about, which is this representer theorem. Representer theorems. So in practice, what usually the situation is the following. So in practice, what you have is that you have a data set, a data set D of input-output pairs. So you have inputs. In our case, these inputs are paths. and outputs, say, are scalar valued, yi. And so these are paths, and these are scalars. And you have n of them, n input-output pairs. Okay, so then what you want to do is that you want to learn the function that maps the inputs to the outputs. And what you do is that you pick a loss function that you like, okay? You know, of these four, let L, so little l is a map from, sorry, is a map from paths times r, and to the power, well, n, I guess, because you have n pairs and tuples to r, that you know, that takes this and you know, takes a path gamma, it takes takes a path x, it takes y, and also it takes, for example, the evaluation of f at x. Some cost functions can also take the evaluation of f at x, usually not, but they can, and outputs, you know, L of x. Sorry. This, so let's make it simpler. Okay, so let's suppose that this is like this. So this loss function takes in the data set, okay, and outputs, you know, something like L of, you know, xi, yi, sorry, x1, xn, y1, yn. It takes all the data and outputs some cost. Right? And this function is generic, right? There's absolutely no assumption whatsoever on it. Just a loss function. Doesn't need to be convex. It doesn't need to be the loss. Right. And then, okay, so then what happens is that, okay, what I can do is that I can define L of, okay, so the data set, this data set f, d depends on f, right? Because this yi are equal to f of xi, right? So this data set is somehow depending on f that is not known, but it depends on an underlying function f. And so then what I can do is that I can consider a loss function. I can look at this a loss function that depends on f, right? L of f, and define it as L, little l of the data set f. Okay. And then, okay, so in optimization, in machine learning, what you do is that, okay, then you take your favorite type of functions. So you take the minimum over your favorite space of functions. If you're in deep learning, you take f to be in the space of neural networks. If you are in kernel methods, you take f to be in the RKHS, okay? F to be in the RKHS of your kernel. It depends on D, so otherwise. And you minimize this loss function, right? That's usually the optimization that you're trying to solve. And again, this L is generic. There is no a priori assumption to it. And then the theorem, the representer theorem, tells you that if this optimize, so if, you know, if there exists a solution to this problem, to this minimization problem, then this solution must then, so let's call this F star. So F star is the argmin of this optimization. Then this F star must be a set A, where A is the set of kernel evaluations, so k phi xi comma dot, where the xi are the training points. So xi are your, training points. Okay, so there is no, sorry? Span, yes, thanks, thank you. Thanks. Okay, so that's it. So there is no gradient descent, there is no optimization in some sense. Well, there is an optimization in the sense that, in other words, f star evaluated at a new point is going to be of the form I equals 1 to capital N, alpha I, k, x, I, comma, x. So there is an optimization in the sense that you need to find the alpha I, but this is a linear regression, right? It's not complicated. You can solve it in various ways. Okay, so that's somehow the nice thing about kernel methods is that in general, the optimization is not the bottleneck, right? I mean, having guarantees that the optimization that you're solving can be written explicitly in this way is not the bottleneck. Whilst it can be for neural, it is for neural networks, right? For neural networks, you run your SGD and you hope for the best, but you have usually no guarantee that you would get there. Whilst with kernels, the optimization is explicit. It has a closed form solution. So for that, that's good. And okay, so the proof of this is classical. So I'm not, especially because I'm looking at the clock, so I'm not necessarily going to do it. But it's very easy, right? So you just take, essentially you take f, you take, you say, okay, the whole space is just the whole space of functions h that you want to optimize over is just equal to a plus a perp, the orthogonal complement of a. And so essentially you can decompose any function in the RKHS as, you take f tilde, you can decompose it as a sum of f plus g, where f belongs to here and g belongs to there. And then what you do is that, so actually here I forgot something, is that this optimization is, this L is actually a regularized optimization. So this is, you need to add the regularizer. So f h. Okay, so you have the loss function here plus a regularization. But anyway, so okay, you have this. You can decompose the h, any element of h in this way, and then essentially what you do is that you realize that L of f hat is just L of f because G annihilates all the points in your data set, right? So the loss function, it doesn't see the orthogonal part. And then the second step is that essentially if you look at so the second part here, this is squared, I guess. If you look at the RKHS norm of f hat squared, this is always bigger than the RKHS norm of f because you're always adding a bit to it, right? So adding an element of the orthogonal complement makes this optimization worse always, right? That's it. That's the proof. That's, L of f, it doesn't see the G, and the other parts, the regularization, always gets worse with G. So that's it. So the optimum must lie in A. And yeah, so that's that. And so perhaps as an example, if you take, for example, regression, then you will have that L of f is going to be equal to 1 over n, the sum equals 1 to n of yi minus f of xi squared. So that's your mean squared error. So that's the loss. And then what you do is that you know that the optimal looks like this. And how do you determine the alpha I? Well, you can do several things. You can run gradient descent, where you have a convex function in this case, so it will converge nicely to the right global minimum. Or you can solve it exactly, right? So you just plug this f star back into your optimization. And what you get is that you get you transform this optimization over function space over an optimization on parameter space. So alpha in Rn. So this is now a vector as big as the data set, 1 over n, the sum of, no, 1 over n norm of y. So this is the vector of all the y's put together minus k alpha. We'll tell you in a second what k is, squared Rn plus the quadratic form alpha k alpha transpose. So where k here is just the matrix of kernel evaluations, right? This is the Gram matrix. Kij is k phi xi xj. Okay, so this is a, you know, you turn this optimization over the RKHS into an optimization over the parameters, right? The linear parameters of your function, and then this is a quadratic, finite dimensional quadratic optimization problem that you can solve exactly, right? You have an inverse and you have a formula for it. Yeah, so, okay, so if I had another 15 minutes, I would have tried to reconnect back the controlled differential equations and the kernels. But yeah, unfortunately, that's not going to happen in 3 minutes. But yeah, if you have any questions, I'm happy to answer them.
Thank you, Chris, for a very nice mini course.